Okay, so this is the continuation of the subtopic in topic 2, numerical solution of linear simultaneous equation and matrices. So for subtopic 2.2, we will cover Gauss-Jordan method, which is actually a variation under the Gauss elimination technique. The learning outcome for this subtopic is to analyze, identify, formulate and solve a set of simultaneous linear equations and other related civil engineering problems using Gauss-Jordan method, which will cover CO1 and PO2. The figure shown here is the graphical depiction of the Gauss-Jordan method. As I stated before, this method is actually a variation of Gauss elimination technique. But the major difference between Gauss-Jordan method and the Gauss elimination method is the unknown eliminated from all other equations rather than just subsequent one, like the previous method. So all rows are normalized by dividing them with their pivot elements, okay, resulting in identity matrix as shown here. So what is the identity matrix? Is when you have 1 for all the diagonal value. Alright, the subscripts n showing n times of elements modification. Now we can look further into the Gauss-Jordan method implementations. So from example 12, use the Gauss-Jordan technique to solve the same system as in example 4 from topic 2.1. Okay, so we have a set of equations here and then convert to matrix form, and I already taken out the unknowns of x. And then for the solutions, first is to normalize the first row by dividing it with the pivot element of 3. So the pivot element of 3 is come from the first row. And then after you normalize the first row, it will become this. Then the step continue with the elimination of x1 term from the second row here and the third row. Okay, this can be done by subtracting the first row times by 0.1 from the second row, and then it will get the new value for the second row. Okay, and then continue with the third row minus with 0.3 times by the first row to get the new value of the third row. Note that we already eliminate the x1 term from the second row and the third row. Next, for the second normalization, the second row is divided by 7.00333, and then the x2 term eliminated from the first and the third row. So we need to eliminate these coefficients and this coefficient. Okay, so for the normalization, as I said before, the second row divided by 7.00333, and then the first row minus with negative 0.03333 times by the second row to get the new equation of the first row, and then followed by the third row minus with the second row times by negative 0.190000 to get the new equation for the third row. Sorry, for the second row. Lastly, for the third normalization, the third row is divided by 10.0120 to eliminate the x3 term from first equation and the second equation. Okay, the normalization of third row divided by 10.0.120, and then followed by the first row minus with the third row times by negative 0.0680629 to get the new equation of the first row. And then the next step is the second row minus with the third row multiplied by negative 0.0418848 to get the new equation for the second row. And then after we determine or we obtain the identity matrix which have value of 1 for all the diagonal part, then we can use the back substitution technique to get the results for x1, x2 and x3. That is all for the Gauss-Jordan method, and now we will continue with the third subtopic in the topic 2, which is LU decomposition method. So for the learning outcome of this subtopic, at the end of this lecture, you should be able to decompose of a non-singular matrix into LU or lower or upper matrix. And then second, to show how LU decomposition is used to find the inverse of a matrix, and to analyze, identify, formulate, and solve related civil engineering problems using LU decomposition method. Now we look at the overview of LU decomposition. Gauss elimination method here can be implemented as an LU decomposition. Okay, this LU decomposition method is efficient in computing a matrix inverse, which can be used to evaluate a system condition. Okay, so when we have a large system of equations, Gauss elimination is inefficient when solving equations with the same coefficients A but different right-hand side constant of B's. The forward elimination step comprises load of computational effort. So this is the problem. And then the LU decomposition method separate the time-consuming elimination of the matrix A from the manipulations of the right-hand side B. Thus, once A has been decomposed, multiple right-hand side vectors can be evaluated in an efficient manner. Okay. Remember the equation 2.40 shown in the previous slides, which is AX equal to B. The linear algebraic equations can be rearranged to get AX minus B equal to 0. Okay, suppose that equation 2.41 could be expressed as an upper triangular system like this. So this equation can be simplified into Ux equal to D for equation 2.42. This is actually similar to the manipulation in the first step of Gauss elimination. And the equation of 2.42, if we rearrange the metric notation, we will get equation 2.43, which is Ux minus D equal to 0. Okay, assume that there is a lower diagonal matrix with ones on the diagonal values. So this is called as equation 2.44. When this equation pre-multiplied by equation 2.43, the result is equal to 2.41 as shown below. This is the equation 2.41 from the previous slide. So if this equation holds, it follows from the rules of metric multiplication that L multiplied by U will equal to A, this equation, and L multiplied with D will equal to B. Okay, we will get this equation. Figure here shows this two-step strategy of LU decomposition solution consists of decomposition and substitution steps. So for the decomposition step, matrix A is decomposed into upper matrix and lower matrix, and then followed by the substitution steps, which consist of forward substitution and backward substitution process. For the forward substitution process, equation 2.47 is used to generate an intermediate vector of D. Okay, and then followed by backward substitution, where the result is substituted back into equation 2.43, which can be solved by back substitution for x. Okay. Now we look at LU decomposition version of Gauss elimination. Okay, actually, Gauss elimination can be used to decompose matrix A into lower and upper matrix. The forward elimination step is intended to reduce the original coefficient matrix A to the upper triangular format of U, and the matrix L is also produced during the step. Okay, this is the lower matrix. The process can be illustrated for a three-equation system of AX equal to B. Okay, first of all, multiply the first row by F21, then subtract the result from the second row to eliminate A21. So we want to eliminate A21. And here the F21 is equal to A21 divided by A11. And then the second step is first row multiplied by F31, which is equal to A31 divided by A11, then subtracted from the third row to eliminate A31. Lastly, multiply the modified second row by F32, which equal to A'32 divided by A'22, and subtract the result from the third row to eliminate A'32. So we are actually eliminating this part. Okay, we can store the F21 in A21. Okay, here, and F31 in A31, and F32 in A32. After the elimination, the matrix A will become this. Okay, this matrix represents an efficient storage of the LU decomposition of matrix A. So we can prove here that A is equal to L, or lower matrix, multiplied by U, or the upper matrix. So now we look at example 13 for a better understanding on this method, which is LU decomposition with Gauss elimination. We need to derive an LU decomposition and generate the final solution for the system below. So we have a system that has already been converted into matrix form, which is equal to AX equal to B. Okay, for the solution, first we need to conduct the LU decomposition process. Okay, we determine the value of F21, which is equal to A21 divided by A11, and then we need to determine the value of F31, which is equal to A31 divided by A11. And then we can do the elimination process of X1 from the second equation and the third equation, and after that we can determine value of F32 by dividing A'32 with A'22. So we can straightly obtain the triangular matrix L by substituting the F21, F31, and F32 from the previous calculation into this metric. Alright, and then we will continue for the second elimination, where the x2 here is eliminated from the third equation. So consequently, the LU decomposition is A equal to LU. So L is the lower triangular matrix obtained from the above equation, and then the upper triangular matrix, which obtained from the second elimination. The result can be verified by performing the multiplication of LU matrix and compare to the original matrix A. So if we can see here, there are discrepancies between the LU multiplication with A. These are due to runoff errors. Okay, and then continue the process with the forward and back substitution step. The forward substitution phase is when we multiply or we rearrange the equation of LD equal to B. Okay, by multiplying out and solve the left hand side of this metric, we will obtain the value of D1, D2, and D3. And then the result can be substituted back into the equation of Ux equal to D. Okay, because D is already obtained from the previous calculation. And from here, we can get, or we can solve the problems by obtaining the value of x1, x2, and x3. Okay, for an exercise of the LU decomposition method, I need you to do this exercise 2, where you need to conduct the LU decomposition method to solve the following simultaneous linear equations. Okay. Okay, last but not least is the metric inverse that can be obtained by using LU decomposition method. The inverse can be computed. Okay, the inverse can be computed in a column by column fashion by generating solutions with unit vectors as the right hand side the right hand side constants. For example, if the right hand side constant has 1 in the first position and 0 elsewhere, so the resulting solution will be the first column of the metric inverse. Okay, similarly, if a unit vector with 1 at the second row is used, so the result will be the second column of the metric inverse. The best way to implement such calculation is with the LU decomposition algorithm as described before. So you can get a clear overview of this process of determining metric inverse using LU decomposition method from example 14. Okay, so I need you to go through example 14 and then understand how they do for the metric inverse determination. Okay, so that's all for topic 2. I hope you can understand, and all the best. Thank you.